Oh my goodness, that's loud. Wow. Hi everyone, welcome. My name is Reza Shadmehr. This is Learning, Estimation, and Control. And good to have you. I'm really happy we got such a nice room, beautiful sunshine coming in. And I got a chance to warm up my jaw because 5 minutes ago when I was talking, I noticed that I couldn't talk very well. Just slurring my speech. So anyway, um, so I was going to this today tell you a little bit about the class, a little bit about myself, introduce to you Sasha. Sasha is our teaching assistant, and tell you a little bit about what to expect in this course. I've been teaching this course probably 20 years. Um, it's a homework heavy course. Uh, I will go through the grading stuff with you, but 50% of the grade is homework, which tells you that a lot of the stuff you're going to learn is based on the homeworks. And the idea is that, I'll teach you the basic ideas in the class, but then you're really going to, I think, learn the material on your own when you're doing the homework. And unlike a course that's been taught only a couple of years, this course has been taught a lot, which means that I think the homeworks have pretty much figured out, all the little details of it. So hopefully it won't cause you much trouble. Um, so let's go over the basics of the course with you. Why do I teach this course? Why have I taught this course? Like anything, you want to teach a course that you want to take yourself. And I wanted to teach a course that basically described the mathematical foundations of some of the most important algorithms in engineering of the 20th century. And why did I want to do that is because in studying the brain, which is what I study, I found formal thinking in terms of mathematics, a very useful way to describe functions of the brain. And those functions are the same mathematics that's used to describe artificial systems, whether it be for learning of artificial systems, whether it be for control of artificial systems, or estimation in artificial systems. These are all the same ideas that come from mathematics and engineering that is being applied to understanding the brain. So for me, the course is about really the foundations of some of the most important ideas in engineering that become involved in what's called computational neuroscience. So as I teach the course to you, you'll learn the math, and then I'll try to teach you the critical papers that use that math to understand something about the brain and use it in a way that hopefully you'll see how do they make discoveries about how the brain works. So, of course, a lot of this math is also used for artificial system algorithms that I'll teach you for supervised learning is the foundation of AI. But our interest is in understanding, the brain, and so we'll see how the math is used in both domains. So the course is called Learning, Estimation, and Control, and as you can see, there are really four major ideas here. We're going to begin with learning, which is supervised learning, and you're going to learn some of the fundamental algorithms that are used in supervised learning. Then we're going to do estimation, and estimation is the process by which you have some model of something, and you take samples from that model, meaning that let's say you have a rocket that's been sent out and you have some model of how when you give it input, it moves, and then you get telemetry from it. And that telemetry tells you something about where it is. And so what you want to do is combine what you expect to see with what you actually saw, your, your predictions with what your observations are. And estimation is something that was formalized by Rudolf Kalman, who was a scientist here. And he described what's called the Kalman filter. And the Kalman filter is probably one of the most important ideas in engineering of the 20th century. So I'll teach you that, which is then the basis of Bayesian estimation. Okay, then we're going to learn about clustering, which is basically a non-supervised way by which you can find, structures and data. And we'll talk about some of the algorithms in clustering. And finally, we'll talk about control. And control, of course, is about doing something, not just observing the world, but actually making things do things. And what we'll talk about is concepts called optimal control. So optimal control is about having a cost function, meaning that I want to achieve something that it would be optimal in some way. you're taking this class presumably because you think it's going to help you down the road. Why? Because you have some long-term goal, get a job, have a happy life. This is a step you're taking. So Bellman wrote a set of equations which are called now Bellman equations. That's the second most important, I think, set of equations in engineering of the 20th century. And the Bellman equations are describing a way by which you can optimize a long-term goal, given that you find yourself at the current state. So today is a cold day. You somehow decided that by going to this class, this was a better idea than, staying at home and keeping warm. So the decision that you made is an attempt to optimize some long-term function. And Bellman described this in a set of equations called the Bellman equations, which is the basis for achieving things like learning to play games where, I'm going to make a move, you're going to make a move. And what I want is that the sequence of actions at the end is going to give me some success. Making decisions based on, say, money, so that I can become, somebody who's wealthy at some point in the future. So unlike supervised learning, where somebody's going to tell me what's good to do now, Bellman equations are a set of rules by which we can guide our decisions so that you can achieve something in the long term. So in a way, if you think of the 10 Commandments, the 10 Commandments are those policies that tell you how to live a good life so you can have an optimal goal, go to heaven or something like that, or have a good life. Bellman equation is the way to formalize that. And its cousin, which is reinforcement learning, is a way to achieve what the Bellman equation tries to do for linear systems. And that becomes the final topic that we're going to talk about, which is the basis of many of the learning algorithms that are used. And all of this links to the brain. We're going to talk about mechanisms of error-dependent learning, reinforcement learning. These are all things that also happen in our brain, and there are, neurotransmitters and systems that are involved in these processes. But what I'm hoping to teach you is that by thinking mathematically about what it is that you're seeing, you're putting yourself in a position to link the work to a larger body of work and formalize what you are observing. So not just the molecules and the neurons and the action potentials, but a broader framework to think about information and how it's being expressed in whatever system that you're looking at. So this is the content, largely just a snapshot of the content of the course. And let me see if you have any questions that I can answer for you. So another aspect of the course is that I'm going to stop in the middle of things and I'm just going to not continue until somebody asks a question. Yeah.
Comes to stuff like, especially like clustering, I use clustering for my own projects and all that, but like what type of data sets or like examples will be given?
Yeah. So let's look at our homework so you can get a sense of that. So here's the webpage where everything that you need to know about the class is. So shadmehrlab.org, if you go to courses and you look up at this course, so here we are. So you'll see there's for today, believe it or not, today you're going to have a homework, which is like, how is this possible? But it's true because I'm going to actually teach you something. And so if you go down to clustering, you can you can look at the homework there, and you can look at the lecture notes there, and you can see the kind of data that we're going to be using to do clustering. And you're going to get a basics of clustering. First, we're going to do linear classification using posterior probabilities. Then you're going to see dimensionality reduction with nonlinear dimensionality reduction, like t-SNE, which I don't know, you probably have heard of t-SNE. And then finally, we're going to talk about expectation maximization, another important algorithm, EM, it's called. Anyway, look, you can see the entire course with all the homeworks and all the data sets and so forth. Thank you for the question. Okay, so let's go back to what I'm going to be asking you guys to do. So let's talk about sort of the mechanics of the course. So as I mentioned, so grading. So the homeworks, 50%. We will only have one exam, and that's the midterm. And that's 25%. And then we have a final, but that's not an exam, it's a project. And this project, I give it to you, and you can guess basically what this project is going to do is going to give you a problem that's going to involve a lot of the things that you've had in the course. And we're going to do an optimal control problem where you're going to have to do estimation. You're going to have to use the Bellman equation and to do it together to then solve a particular optimal control problem. And the final is a take-home project that you're going to have, I think, about 10 days or something like that to do it. So that's 25% of your grade. Okay, so 25, 25, 50%. Our only test is the midterm, and I believe the midterm is March 12th. It's the last Thursday before the spring break. And it's open notes. What that means is that you're allowed to bring a piece of paper with you that has whatever you want on it. Okay? So I don't want you to memorize anything. I just want you to understand what the material is. And you'll get a copy of the exam that was given last year. So you can sort of get a sense of the material that I'm going to go over. Okay. Let me tell you about homeworks. So homeworks are, as I said, 50%. So homeworks are due on Tuesday each week before class. And I think Sasha, should they just email it to you, or how do we do this?
There's links on campus for the events.
Okay. And they in order for them to turn it in?
Also on this.
Okay.
You guys can usually upload zip files so if you're not episode. Or we're going to just scan photos of any of the homeworks that require derivations or written equations.
So you're gonna get the homework today, homework Thursday, it's due next Tuesday. Does that make sense? So once a week, the homeworks are due. Okay. And I know, things can happen. You can have, things in family. You may have interviews at places. So what we're going to do is drop two lowest homeworks. So you don't have to worry about grades so much. I'm hoping with hopefully a fairly generous policy associated with this. So as a result, there are no late homeworks allowed. If you're late, we'll just drop that homework for you. Much of the material that you're going to have is going to require coding. And so I just want to give you a word about integrity. What I expect from you. So works and discussion between people, of course, are fine. You're fine to work with other people. But what I expect you to do is that when you turn in something, it's your work. Okay. And I encourage undergrads in this class. And so we give extra points for undergrads who take this course. And that's 5% for seniors, 10% for juniors. So because many of the people in the course are graduate students, I think of the undergrads as kind of like, GT courses, if you will, for the material. Okay. Any questions about this? Yeah.
The point the campus isn't published yet. When will we see it be published?
That's my fault.
Tomorrow, probably we'll figure that out.
Yeah, I'm sorry about that. Yeah. Thank you. Any other questions? Okay. All right, so what are we going to be talking about? Okay, so we're going to begin with supervised learning. Yeah, of course.
So like say you're an undergrad and you're doing a 3+1, so you take the class as a master class, then obviously the extra credit doesn't apply.
So you are a senior now, or what
The
are you?
junior.
You're a junior now? Yeah, why not? Yeah. Look, I want to give everybody A's. And look, I can tell you, this is a hard class. The homeworks are difficult. And so if you stick it out, if you do the work, why not? I want to encourage you to take the hard classes, and hopefully it'll make hopefully it's worthwhile, something that you'll take with you, and you'll say, I learned something from the course. I mean, I care a lot about it, and I hope that you will too. Any other comments? Like I said, it's a course that I wish I had when I was a student. But that's my opinion. So you may say, I wish I hadn't, but we'll see. Okay, so supervised learning. So the supervised learning basically, is labeled data. So you have X, that's your data, and Y is your label. Y hat is your guess of what X should be. And today I'm going to teach you a simple rule for learning, and it's called Perceptron learning rule. And this is not because it's a particularly important learning rule, but it's just historically, I think it's useful for you to know how did learning algorithms become so predominant. And this was the first learning rule that really took the scientific world by storm and gave a lot of hope that there would be something like AI, like what we have today. But this was in 1958. And I'll tell you a little bit about it. You'll learn that learning algorithm. You'll apply it on some data today. Then we're going to talk about loss functions. So whenever you're trying to learn something, you're trying to match some data, you have some cost that you're trying to optimize. And, typical costs are like this. You take your data and you subtract from it your estimate and you square it. And things like this are called least mean square. So you're minimizing the squared error in your estimate. And the sum here is over your data points. So we're going to talk about loss functions. And I'm going to ask you questions like, we're going to talk about some interesting things like, what's the loss function for your brain? It's a learning machine. Is it a squared error like this? Why do we use squared errors? What does this mean? And so it's interesting because, you can ask, we have a learning machine here. What might its loss function be? And people have done experiments about that. And I'll show you some ideas about it. Then I'm going to teach you the Newton-Raphson technique, which is a way to minimize loss functions using gradients that has both first and the second derivatives. Then you're going to learn the very famous algorithm backpropagation, which of course is the foundation of all AI today. But we're going to learn the original paper that described this work and the original algorithm, the way it was done, and the application that they used it for. And I'll try to teach you also how people use it to understand something about the brain, how they use it to try to understand neural representation, in this case, in the posterior parietal cortex. Then we're going to learn maximum likelihood. So maximum likelihood is an idea that you have some data and you have a model with parameters theta. And what you do in maximum likelihood is that you want to find theta so you maximize the probability of the data given your parameter. So you have a likelihood. Likelihood is a probability. And in this case, the probability is probability of observing something, the data, given that I have this parameter that I don't know what it is. And you find the parameters that maximize the probability of observing the data, maximizing the likelihood. That's called maximal likelihood. And we'll apply it to some of the some data so you can see examples of it. The next topic I'll teach you is called estimation theory. And this is the Kalman filter. And now, instead of just having static systems, X that maps to Y, now we're going to have dynamical systems. So in dynamical systems, what we have is typically, say a linear system like this. So this is showing you that the state of the system, X, which may be hidden to you, is changing by some input, U. There's some noise that affects that change, and it becomes a new state in some step in the future. You may not be able to observe these states directly, but maybe you can observe it via this equation. So this is what you measure. So you have a dynamical system like this. So this could be your arm. This could be some system that you're trying to control, a rocket that's flying. You give it some input, some activation to your muscles, the body moves someplace. You have some sensors that provide you with feedback. And the problem is to estimate. Let's see if I know how to do this. Oh, that's the eraser. Wrong one. Highlighter. Where's my highlighter? So you can see that I am new to this business of using this. Hisham, where's my highlighter?
Should be the third tool.
There we go. Yeah, okay. That's what I wanted to do. So that's the next state. And that's what I'm trying to estimate is the state of the system here, X, that I can't observe. Okay, so what estimation theory does is to say, what's your guess about whatever it is that you're trying to estimate? What's the observation that you made, and how should we combine them? And the idea is this, that if you're really confident about your guess, then it doesn't really matter what you measured. Your guess is what matters. But if you're not confident about what you're guessing, then you should take the observation. And it's really the difference between a person that has uncertainty versus a person who's confident. So to make a political statement, if you're Trump, you are right all the time. So no matter what I guess about the world, the data doesn't really matter because I know I'm right. The observation doesn't matter. But if I am uncertain about what it is that I'm observing, then I'm going to make a guess about something, but then I'm going to take the data, and then I'm going to move toward the data by some amount. And that amount that I move is about my uncertainty. And so what the Kalman filter does is to mathematically define this concept of uncertainty. So remember that at the beginning of the course here, I was saying that, look, you're going to have a guess, right? So here's your guess, right? Here's your guess. But your guess isn't just a number. It is associated with it some measure of uncertainty. How confident are you about your guess? And what the Kalman filter does is to organize these ideas into mathematically representing uncertainty, observation, prediction, and how to combine them. And that becomes what's called a common gain that puts these two things together. What I observed, what I predicted, and then how much should I change my belief based on my uncertainty. So that's the idea of a Kalman filter. Does that make sense? Okay, so and I'll teach you that. And I think it is probably, this idea is probably one of the most important ideas in the mathematics of engineering of the 20th century, which is what Kalman did, which then becomes the basis for Bayesian estimation. Okay, so then the next topic, indeed, Bayesian estimation. So now remember, when we were talking about maximum likelihood, I said maximize the probability of the data given the parameter that you're looking for. In Bayesian estimation, you maximize what's called the posterior probability of the parameter given the data. And this relates to the Kalman filter because maximizing a posterior probability depends on having priors. Priors are like your beliefs. What do you think the world is like? And those priors are not just means, but they're distributions. This distribution is the uncertainty that you have. How wide is your distribution? Yeah.
I always have trouble understanding likelihood and probability.
Uh-huh.
And like,
Yeah, absolutely. So likelihoods are conditional probabilities. So I guess because of Zoom, let me write it down here. So a likelihood is probability of, in the context that we're talking about, probability of data given some parameter, theta. So for example, it would be if theta is the mean and the variance of a distribution, and if it's a Gaussian, then the probability of the data, so here's the mean, here's the variance, the probability of data is, here's your data. How far is it from the mean, right? The farther away it is, the less likely it is. So likelihood requires a model. It requires you to have an understanding of, where your data comes from. Yeah.
How would it look like if your data has, instead of like one parameter, it could be that distribution has like 2 or 3?
Yeah. So a multidimensional vector, for example. So suppose it's a 2-dimensional system, like this, right? So still, I now have a 2-dimensional space that describes the probability of something with respect to, the maximum location. So it's still a distribution. It has some value. So if it's far away, it's less probable. So what this means is that you have a model that describes the likelihood of observing data. And so if I observe the data point here, it's pretty reasonable that it came from this model. But if I observe the point way out here, then it's really unlikely that it came from that model, right? So likelihood tells you how likely it was that your data point came from the model that you think generated that. And indeed, all the examples that we're going to do in class are vector-based systems. So you're going to have multiple, the value associated with the vector. Okay, so that's Bayesian estimation. Then we're going to do clustering. So clustering is based on the idea that is there some similarity between the data? And often the data is in high dimensions. So there may be 30 dimensions. Well, I can't see what the 30 dimensions look like because I can't observe 30 dimensions. So what clustering begins with is dimensionality reduction. And one of the principal tools is called principal component analysis. Which is a linear form of dimensionality reduction. This minimizes a cost that we can describe for you. So PCA is one of the things that we'll learn, And then we'll learn another more recent development. It's called TSNE, which is nonlinear form of dimensionality reduction. It depends on, it brings things together based on their local value. And this is the basis of the a system that's used very frequently now. It's called UMAP, which is based on TSNE. Anyway, I'll teach you that. In fact, TSNE and backpropagation are both made, they're both invented by the same person, Jeff Hinton, who last year won the Nobel Prize in physics, of all things, for this work that, for backpropagation. He won the Nobel Prize. Okay, so under the framework of clustering, we're also going to learn about a algorithm called expectation maximization, EM. And EM is a really powerful algorithm that another one of those magnificent developments in the 20th century, which is related to clustering, because oftentimes you don't know how many clusters you have and you don't know where they are. And so you have two kinds of problems. I don't know how many, and I don't know where the clusters are. The typical problem of EM is the following. You have some model. So say you have a dynamical system. And I make some observation. So I'm going to underline the things I know. I know the input and I know the observation. So I gave the input U to this system. I made an observation Y. I don't know X, which is the state of the system, and I don't know A, B, C, and the noises. So I don't have a model of the system, and I don't know the internal state of the system. Internal state of the system is X. The model is those parameters, A, B, C. All I have is the input that I gave and the output that I got. Input that I gave was U, output that I got was Y. What EM allows you to do is to solve this problem and find both the states, X, and the parameters, A, B, and C. And the way it does it is by using the Kalman filter to find X. And then once you find X, find the parameters A, B, and C. So it's a recursive algorithm that lets you go back and forth. You'll see how to use it for this purpose. So it's a powerful system. Any questions so far? Okay. Finally, I'll teach you about optimal control. So optimal control is the idea that, let's take the system here, this dynamical system here. Well, I don't want to just understand how it works. I want to do something with it. So I want this system to perform some final behavior. And if you think about your body is a dynamical system. You give it inputs, it does things. And the idea is that, how do I do things optimally? How do I walk in a way that I minimize the energy consumption? How do I apply these equations to make decisions so that I become a happy person? Optimality is about having some eventual goal, but you find yourself in this state. What is the best action you can do now to get to that eventual goal? The example that I like to give is that, say you want to retire. I want to someday retire when I'm 35 years old in Hawaii. Okay, so that's my goal. How do I get there? I need to know what is the best action that I should do to actually get there. And so what optimal control does is to give you policies. What is a policy? Policy is what is the optimum action that you can do if you find yourself at this state at this time. So it provides you with the optimum action at this state in order to optimize this long-term goal. So think about it as playing a game. Say, if you want to learn to play Go or chess, there's a state. You look at the board, that's your state. What's your goal? To win. So if the future goal is to win, but I find myself at this state, what's the optimum action that I should do? That's U. U of X is the optimum thing you should do. So we'll apply it to dynamical systems. So for example, if I move my arm from here to here, what's the best way to do that? Is it this? Is it this? Is it this? What's the best way to get there? There are many ways to get there. So when you think about your brain, you have goals. Pick this up. But what you don't have is a teacher that provides you with all the details of how to do it. Yet somehow, your brain knows what's the optimal way to do it. If you have a muscle ache, like I have today, the best way to get there may be different than yesterday when I didn't have the muscle ache. And your brain figures that out. So I want to take those ideas, mathematically describe them, and teach you how to solve those kinds of problems. So this is related to playing games and the concept that we're going to end with, which is reinforcement learning. So the difference between reinforcement learning and supervised learning is that reinforcement learning, you have no teacher that provides you with intermediate feedback. You just have to do it. And at the end, you look at the cost. At 35, are you living in Hawaii, retired or not? And if you didn't, you have to figure out how you should improve your decisions so you can get them. That's what reinforcement learning is. And that's a way to do optimal control. And I'll teach you that when we get to reinforcement learning. We won't be able to solve the problem of Hawaii in 35, but we'll be able to do some other games with reinforcement learning. But you can sort of see how these things have tremendous implications. If someday we have models that describe dynamics of your body, you can really figure out what's the best way for me to do anything. And policies are the conclusion that comes from reinforcement learning. Policies are the conclusion that comes from Bellman equations, which is a way to do optimal control. And as I mentioned to you, the way I think about like the 10 Commandments are policies. Thou shalt not do this, thou shalt not do that. Why? Because if you follow those policies, you're probably going to have a better life than if you didn't follow them. And policies are indeed what comes out of the Bellman equations. Okay, questions? Yeah.
Maximization. In situations where noise is like substantial or where you see it might restrict your estimations to like some local maxima, like how is that kind of just a weakness of expectation maximization, or is there some way to handle that?
Yeah. There's no way getting around systems that provide you with a very difficulty to observing its state. So if the observation that you're making, Y, is based on a lot of noise, you really are being forced to make a lot of guesses. And yeah, you're not going to be able to build a very good model, basically, of that system. And if you do build a good model, well, it probably is because just this version of it worked well. That probably won't generalize. Yeah. So, noise, the one way to think about it is that it just wasn't a very good model because it's not capturing the underlying dynamics well. That's what it's telling me. Okay. All right, so let's do a little bit of actual useful work this morning or this afternoon. So I'm going to teach you the perceptron learning rule so you can apply it to the homework for today, which is going to be to do some classification on a bunch of features that describe Netflix movies and whether it can make good predictions about whether you're going to like this movie or not. And if you do that and if it works well, then there's a the homework, an additional homework. Let me just show it to you. Here it is. So the additional homework is this extra credit, which is handwritten digit classification. If you want to do that, you can also use this perceptron learning rule to try it on that. Okay, so what is the perceptron learning rule? So in 1958, there's this guy called Frank Rosenblatt. And like many people, they're interested in the brain. They're interested in understanding how do we represent the brain. The digital computers are becoming available, and they think about the process of learning. And Frank comes up with the following depiction of how a learning system might work. So he's got an input X, which are called features. And so this, imagine there are these multi-dimensions that describe features of something. So if you want to think about it as a movie, features of a movie, and you could have X1 be romantic or not, X2 be something about the location, whatever are the features that describe the movie. And they could be analog or they could be digital. So they could be 0 or 1, binary, or they could be real valued numbers. And then Y is the output, and that's the label. So, and in this case, what we're going to say is that Y means 1, which means I will like it. I will like this movie. And 0, I won't. So the idea is to try to learn whether this movie, which has these features, are going to be palatable for me. Should I recommend it for you or not? Okay. Okay. So what Frank did, he came up with a learning rule for this. Sorry. Let me. I made a mistake here. This is -1, and that's important. That is not 0. It's 1 and -1. So Y is this limited set. And error, which I'm going to call E, is the difference between what you observed and what you predicted. So did I like this movie? That's what you observed. Y hat is what the system predicted. And how does this work? So the idea is that you have these inputs that come in, X1, Xn, each has a weight. They're all going to sum. And we're going to look at the sign of that addition. That's going to be my prediction. And what you're going to do is then compare your prediction with the observation, Y. And the difference between the two is the error, which then goes to teach and update the weights of this network. So Y hat is the sign of W transpose X, which is the sign of this sum. So the sign is either positive or negative, +1 or -1. Okay, so how are we going to learn this? How are we going to improve W so that next time it's closer to the way it should be? So we have a data set. Here's a movie Here's your, whether you liked it or not. Here's another movie, and whether you liked it or not, and so forth. So this is our data set that we're going to be using to learn. X is a vector, Y is a scalar. X is that vector of features. Y is whether I liked, where I gave it a +1 or a -1. Okay, so we want a learning group. So how we're going to do it? So let's see how we should do this. So here we have this vector X that describes some features, and then we have this other vector W. And then when we do W transpose X, what are we doing? We are projecting it onto this vector X. So W transpose X is the magnitude of the vector W times the magnitude of the vector X times cosine of the angle between them. So here's the angle, theta. So when I'm projecting W onto X, sometimes I get a positive value like this. This is the positive value. W transpose X is proportional to it. And it's a positive number as I've drawn it. It could also be negative. So I could have X, and here's W. And when I project it now, I get a negative number. So the sign of W transpose X can be negative or positive. So what's the learning rule? So if Y is equal to Y hat, then do nothing. That means that if you guess right, if you guess that I'm going to like this movie and I liked it, you don't do anything. If you guess that I didn't like this movie and I didn't like it, then you don't do anything. But what's interesting is what to do when you made a guess and you're wrong. So now there's an error. So what should I do? So let me describe it to you from the perspective of these vectors here. So suppose if Y does not equal to Y hat, we have an error. So what that means is that I need to change W by some amount delta. So W was tilted toward X so that W transpose X was positive, but it should be negative. So that means that I need to take W and add to it a vector delta so that it becomes tilted the other way, away from X. And what I need to know is what this delta should be. So in the case of here, in the case of when Y hat was positive, when sine of W transpose X was bigger than 0 and error occurred, then what I should do is add delta so that W transpose X becomes less positive or more negative. And that delta is something that's going to be proportional to minus X. So it should be opposite of X. Let me stop for a second and see if this makes sense to you. Okay, so W and X are in the same direction because when I project them on top of it, I get a positive number, right? And that was wrong. So I need to change W. I'm going to add to it a vector delta. That delta, same dimensions as W, and which is the same dimension as X, it should be opposite to the direction of X because I should make W pull in the opposite direction. So in this case, delta should be proportional to minus X. Now, this minus here, how is this related to error? So in this case, what we have is that Y was -1, whereas Y hat was +1. So I should have said, you will not like this movie. But what I did say is that you do like this movie. You will like this movie. So the error is Y minus Y hat, which is -1 minus a +1, which is -2. So delta is proportional to error, Y minus Y hat. So I wanted this negative sign times x. I wanted a negative sign in front of x, and I can get it if I write that negative sign as y minus y hat, the difference between what I observed and what I predicted. This is for the case where I have a positive projection. I said you will like this movie, but you in fact didn't like this movie. So what this says is that I should change my W by amount delta, where delta is error times x. Okay, now let's look at the other side. So now let's consider negative number. I'm going to use red. So I want to change W here. So I was predicting something, W transpose X, and W transpose X is here, is negative. So what I want is that I want to change that by some amount delta. And it should be in the positive direction of X. So now delta should be proportional to plus X. How do I get that? Well, let's look at the error. So I predicted that you will not like this movie. Y hat was -1. W transpose X, the sign of it was -1. I said you won't like this movie. But in fact, you do like this movie. So the error is Y minus Y hat, which is 1 minus a -1, which is +2. So that means Y minus Y hat gives you a positive sign you wanted. So delta should be proportional to Y minus Y hat times X. So for both of these systems, regardless of my error, I get the same learning rule. Regardless if my error was negative or positive, the learning rule is the same. And the learning rule is this: change W n plus 1 is W of n plus something that's proportional to Y minus Y hat times X of n. This is a vector, this is a vector, this is a vector, the rest are scalars. Yeah.
Why was it important that you specified that the two cases have to be 1 and -1?
Okay. 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 So why should it be
1 and -1 and not 1 and 0? It's still preserves the image.
okay? So because if in one condition the output is 1, the other condition the output is 0, would this work? So let's see, if the output is 0, then what happens is that so this is a linear classifier. Your decision boundary becomes at 0.5 rather than at 0. So the way I did it, my decision boundary it's halfway between these two, right? So every time you have a W, you make a guess. If it's in the world that I did, if it's bigger than 0, you say the sign of it. So you couldn't use the sign anymore. You'd have to use this. You'd have to say if it's bigger than 0.5 or less than 0.5. That's how. Yeah. Was there a question? Okay. So Perceptron. It's a very simple rule. And it's a linear classifier, meaning that it's saying I'm going to assign weights to your inputs. Based on those weights, I'm going to project it to some output, which means that basically you're going to have some data, and you're going to have this data, if it's separable by a line, is going to be how you're going to say classes A and classes B. Like, not like. All right. So in 1958, this algorithm was proposed. There was a lot of interest in it. People thought, oh, maybe this is the way by which the brain learns. Then in 1969, there was a book written by Marvin Minsky and Seymour Papert. And they showed the fundamental limitations of the perceptron. And here's what they said. They said that, look, you just described a linear classifier. So if you imagine that you have X space here, X1, X2, and you have some data, and the colors are this, y is equal to -1, y is equal to +1, what you're learning from this is a function that will separate these systems. This is W transpose X when you learn it. And if it's linearly separable, then you can learn it. But what if it's not linearly separable? So can you think about a bunch of data now that you can put on the blackboard that is not linearly separable? Can you think of one? Yeah? You want to do it? Show me.
XOR function.
Well, can you draw it on the screen? Can you put it on the blackboard? Good. Okay, so let me draw it for people on the Zoom world. So what was your name?
Daniel.
Daniel, thank you for that. So what Daniel drew is something like this. Basically, he put a point here, he put a point here, then he put a point here, and he put a point here, and he said there's no linear function that can separate the blues from the reds. Right? Okay. So we can come up with lots of things like this. So suppose I do a function that looks like this. I'm going to put some blues here, and I'm going to put some reds here. Well, here's another pattern. You can't separate the reds from blues, right? The donut, for example. Okay, so what Seymour Papert and Marvin Minsky did is exactly this. And they said, well, look, this is great. It's a linear classifier, but there's a whole lot of functions that it can't learn. And believe it or not, that killed the whole field of learning. So there was all this excitement, killed it completely. And nothing was done on this. And now if you think about it, actually, it wasn't that difficult to solve these problems. Here's what you would need to do. You would write a function like this. So instead of W transpose X, what if I have W transpose G of X? So some nonlinear function of X. So for example, I could have a bunch of Gaussians here, like this, two-dimensional Gaussians. And if I use a nonlinear transformation of the input space, then I could separate these things. And so it wasn't that, learning systems couldn't do it. It just meant that the linear learning system couldn't do it. And in 1980, I think it was 88, which is where we get backpropagation, which is if you have nonlinear functions in a network that get some input and want to provide you with some output, how do you learn the W's in between these hidden layers? And that became a paper that revolutionized AI. Until then, before backpropagation, what people thought about as AI was basically what was called expert systems. Expert systems were you would go interview somebody. Say you were an expert in running a nuclear power plant. I would learn everything I could from you, and I would write that down in some form of text, bunch of rules. If I see this, I do this. If I see this, I do this. And those rules became knowledge bases by which databases were generated. The holy grail of expert systems were translating articles. And now, of course, AI translates articles on your phone. You can walk around and you can talk to people and it will translate them for you. So learning systems began with the perceptron learning rule, like you saw here. Its limitations was shown by Marvin Minsky and Seymour Papert. And in fact, I will show you how backprop was then used to learn something about transformations in the brain. So what does this have to do with the brain? Zipser and Anderson, I think it was 1994 or something like that, used backpropagation to say something about the posterior parietal cortex. And so what they said is that here's a part of the brain that we know gets these kinds of inputs, and we think some other part of the brain has a representation that looks like these outputs. We don't know what the heck is happening in this posterior parietal cortex, but if we take a neural network and we take these inputs and we say these outputs are needed, these hidden layers look like these neurons that we found in the brain. So they said we can use backpropagation to understand encoding in the brain. And I'll show you how they did that and their results. Okay. So you have homeworks for today. Look on the webpage and download them and do the homework. And if you have any questions, I'm happy to answer them for you. Yes, sir.
One quick question for the homework. So, what it said, I saw it said like MATLAB and all that.
Yeah.
First, like normal homework, there's no programming language specifics. So, like, can we use like Google Collaborate or like?
Sasha, what do you think?
However, Python for fine. For Python, if you can then Google Colab or Jupyter Notebooks will be fine. Anyway, you can have it. As long as I can run it simply, then it's acceptable.
Oh.
Yeah.
In the formula you provided above for the updating the weights.
Yeah.
Is that N the learning rate?
Yeah, Ada. Yeah. Yeah. What should it be? Well, actually, there is theory behind it, and you'll see it when we learn about Newton-Raphson. You'll see that it's not arbitrary. If you've ever tried these things, if it's too big, it'll explode, right? If it's too small, it takes forever. So what's the right one? And I'll teach you about that when we learn about Newton-Raphson. But I think for the homework, I give it to you, so you don't have to guess it. But there's actually a theory behind how to set it.
I have a question. Could you explain why it requires perfect separability again?
Well, it doesn't require perfect separability, but there is no separability here, right? Anything is as good as anything. Similar to this.
Oh, so just separability has to exist.
Yeah. Basically, it's a wrong model for that problem. And it's just specifying that when you use Perceptron, you're assuming that the underlying data is linearly separable. Otherwise, why the heck are you using it? And the way to think about it is that if you have a 10-dimensional vector of data, you don't know if it's a linearly separable model would work or not. What I would do is first you do dimensionality reduction. Well, what if I look at this in 2 dimensions? Is it separable in 2 dimensions? Is it separable in 3 dimensions? Can I see clustering? Then I would know what kind of model to use. All right. Thank you, everybody. I'll see you Thursday.